Right, we're going to deal with irreducible complexity argument. Who is the author? Who coined the term irreducible complexity? And what was the title of his book? Here's the book. Significant title. We even discussed the title. This is Michael Behe. Okay? And of course, one of the main things that Michael Behe is going to discuss, he's a biochemist. So we can excuse Charles Darwin. Why? As you can see from the title of the book. Why are we excusing Charles Darwin? What's a black box? Remember? It's a whimsical term dealing with something we see. It's exterior. We see what it does, but we have no idea about the inner workings. Yes? Yes, so Darwin's black box was the cell. And a lot of what Michael Behe deals with, and we're going to talk in detail about it, is this living organism right here. Anybody know what that is? That's a bacterium, okay? In fact, that's a bacillus type of bacteria. It's a rod-shaped, and it has a whip-like projection called the flagellum, right? And so Michael Behe is going to use the bacteria flagellum to illustrate and kind of show that living structures are irreducibly complex. So here's Michael Behe, and there's, of course, this is the second edition of his book, first edition published in 1996. I think this edition is 2004, 2003. This is the second edition of the book. And remember, we can excuse Charles Darwin. Why? Because to him, the cell was a black box. He had no idea of the inner workings of the cell. He had no idea what the cell was like inside, how complex it is, and how full of what Michael Behe calls little molecular machines. Okay, so remember what a black box is. It's any system or structure whose inner workings are unknown. Charles Darwin had a rudimentary knowledge of cell biology. Of course, he's lived in the mid-1800s. Darwin's black box is the cell. And according to Charles Darwin, the cell was just a simple living structure. But in fact, the cell is extremely complex. Even the bacterium, that picture that I had up earlier, is a very complex cell. Kind of in your mind, I want you to have the idea that there's basically no such thing as a simple cell. Life, even in its smallest stages, I guess, or the smallest structures, is not very simple. Here it is again. And remember, what is intelligent design attacking? Which mechanism? Michael Behe is basically an evolutionist. He has no problem with basic evolution, which means common descent. He also has no problem with the Earth and the universe being billions of years old. He's still an evolutionist. He's attacking the mechanism of gradualism or neo-Darwinism. As you can see here, we have, I guess I'll go with the laser pointer, numerous successive slight modifications. So we can't account for the complexity of the cell with numerous successive slight modifications. That's a quote from Origin of Species. All right, so gradualism. What's the specific name of Darwin's main contribution? What is it? Yes.
Natural selection.
Natural selection. So natural selection looks good on the surface. It might explain microevolution, but the deeper you get into biology, the deeper you get into genetics, molecular biology, biochemistry. Biochemistry is Michael Behe's specialty. He is a professor of biochemistry at Lehigh University. So the deeper you get into biology, the more complex it becomes, to the point that gradualism is ridiculous. We can't explain how these structures came to be in numerous successive slight modifications. So what is irreducible complexity? Irreducible complexity is one of the best arguments that the intelligent design movement puts forth. And so I want you to understand it. Let's just take the words apart. Irreducible. What does that mean? Irreducible. Cannot be broken down into smaller parts if it's a structure, or smaller steps if it is a process. So remember, when we're dealing with intelligent design, living structures or processes are too sophisticated or complicated, too complex to be the result of numerous successive slight modifications. Gradualism is an unsatisfactory mechanism. That's Michael Behe's point. That's the point of many of the intelligent design proponents. So irreducible is a very good word choice. We can't take a structure and break it down into parts that could evolve one at a time. We can't take a living process and break it down into steps that could have evolved one at a time. Most of our biological processes are controlled by and involve proteins. We can't even figure out which protein could evolve first. We can't even figure out how it could occur by numerous successive slight modifications. This is an excellent argument against evolution. Evolution in particular, or evolution in general, gradualism or Darwinism in particular. We can argue about the age of the Earth in geology. We can argue about, is radiometric dating flawed? We can argue about what are the assumptions made. But this argument is very difficult to counteract, okay? And so I want you to especially pay attention to it. So just taking the phrase irreducible complexity, you can understand what it means. What it means is we can't take a living structure and reduce it into parts that could evolve one at a time, okay? This will be a required essay on the final exam. I'm not going to let you choose, okay? I'll let you choose between the other two, but not this one. So, irreducible complexity, understand the overall idea of what it means so that you can write an intelligent essay from it, and this is a very good argument. So, just let's start with the words. What is irreducible complexity? Why did Michael Behe call it this? And first and most important is that adjective, irreducible. It cannot be broken down into smaller parts or steps and still function. So we've got two ideas here. We can't break it down into smaller parts if it's a structure or smaller steps if it's a process and still have the structure function or still have the process work. So that the implication there is that it can't evolve one step at a time. Do you understand that? It can't evolve one step at a time. So the main mechanism that Charles Darwin is famous for is natural selection. Can natural selection choose something that does not function? No. So it eliminates Charles Darwin's main mechanism. Very important argument. So we've got irreducible. Can't break it down into the numerous, successive, what kind of modifications? Slight. Okay? So here's reducible complexity. Here's what it means. Something is so elaborate that it cannot be broken down into, look at the term here, useful parts. Why is that important? We can't break it down into useful parts or useful individual steps. Why is that word useful important? Why? I just said it. Why is that word useful important? Why am I poking at it with my pseudo laser? That's hard for me to control. Why is it important? So get the argument down and then stop and think about it. Irreducible complexity has the idea that something is so elaborate that it cannot be broken down into useful parts that still function. It must be produced as an integrated whole or an integrated system. I'll give you a second to write that down so that we can think it through. And then I'm going to be repeating this over and over again so that you understand the argument. And then once you understand the argument, the basics of the argument, I can illustrate it with the living structures that the intelligent design is talking about. So let's go back to this word useful. Why is that critical? We can't break down a living structure or a process done by a living structure into useful parts that still function. Why is that word important? What's the mechanism we're attacking? Natural selection. Can natural selection choose something that is not useful? It goes directly against the idea of natural selection, or the so-called phrase that is used commonly is survival of the fittest. So if the structure is not useful, it will not evolve. Why won't it evolve? Natural selection won't choose it. So what we're doing is we are attacking the mechanism very specifically and very efficiently. Okay, so here is the IC, or irreducible complexity argument stated. The irreducible complexity argument is that living structures and processes are too complicated and sophisticated to be the result of the accumulation of small changes. There's the formal statement of the irreducible complexity argument. Okay, Michael Behe actually coined the phrase irreducible complexity. So living structures and processes. It can be a structure or a process, and we're going to illustrate it with a living structure, the bacterial flagellum, and then two processes, the blood clotting cascade and the complement cascade. Both very important, especially the blood clotting cascade processes. So we're dealing with both living structures and living processes. Are too complicated and sophisticated. Those, of course, would be synonyms for the word complexity. So living structures or processes are too complicated or sophisticated to be the result of an accumulation of small changes. That, of course, would be the third step in the mechanism of gradualism. Do you remember the mechanism of gradualism or neo-Darwinism? What is step number one? Variation by mutation. And we're going to attack that on December, what's the date? I guess December 8th. And then the second step is natural selection, choosing the best genetic combination. And what's the third step of gradualism? Accumulation of those small changes. So the idea is that mechanism does not work. That's the whole crux of this argument, is that gradualism or neo-Darwinism, that mechanism does not and cannot work. Okay, 2 requirements for a structure or a process to be considered irreducibly complex. 2 requirements for irreducible complexity. The first requirement is that it has to have several not independent, but interdependent parts or steps. We have to have several interdependent parts. Okay, so what I'm dealing with here is we have to have a set of at least 2, usually many more than 2, interrelated parts, and the parts are closely matched, and they're going to be put together in a very specific way. So several interdependent parts, at least 2, but most of what we're dealing with is many more than 2 interrelated parts or two or more sequential steps. Okay, so remember, it's both living structures or processes. We're going to talk about the blood clotting cascade. So we have two or more interrelated parts or sequential steps. And then these parts are closely matched, or the steps have to be in a particular sequence. That's the first requirement. And that kind of has the idea of it being complex. And then the irreducible part is that the second requirement, the required parts must be present to function. Now there may be a structure or a process, and of course there are structures and processes that have parts that are not required. Okay, so the necessary parts in the intelligent design argument here, and it's the irreducible complexity argument, many times the required or useful parts are referred to as the structure's irreducible core. Many structures are going to have extra parts and extra steps that it'll still function without. Some do, some don't. So the required parts or the irreducible core must be present to function. But do keep in mind that not all parts may be irreducible. So two requirements for a structure or a process to be irreducibly complex. You have to have several interdependent parts or sequential steps, and then you have to have those required steps or parts present or you lose functionality. The required parts must be present for the structure to function. The steps must be in order and working for the process to function. That's the two requirements of irreducible complexity. Okay, what happens then? What are the results of irreducible complexity? What is true about a structure or a process that is irreducibly complex? When we see irreducible complexity in a structure or a process, it's going to result in complete integration, minimal function, and no independent function. Complete integration, minimal function, and no independent function. And as you can see, I've got subpoints. All right? The first one is important. We have to have complete integration. I mentioned this earlier with just the crux of what the irreducible complexity argument is. It has to evolve all at once, because the individual proteins in a biological process don't function on their own, and they don't have an independent function, which is the third result. So complete integration has the idea that the structure has to evolve all at once, or the process has to be complete all at once, or it will not evolve. So the structure has to be produced as an integrated whole, or the entire process has to be present, or it won't function. So complete integration is a result of irreducible complexity. And of course, that means that it must evolve at the same time, or we're going to cancel out natural selection. So if it's irreducible complexity, it has to be there all at once, or it doesn't function, so natural selection cannot select it. That's what we mean by the idea of complete integration. We're going to talk about the bacterial flagellum in a minute. Either we have the entire flagellum all at once, functioning properly, or it can't evolve. Why won't it evolve? Because Charles Darwin's natural selection can't choose it if it doesn't function. It has no survival advantage. So you've probably heard in the past that natural selection, the in-between stages, are going to be eliminated by natural selection, and here's why. We have to have complete integration or natural selection does not operate. Minimal function, what does that mean? This goes also back to the idea of natural selection or survival of the fittest. Minimal function has the idea that it has to be an efficient process that works well, or it won't evolve. Okay, it has to have what's called minimal function, meaning it has to be the simplest, most efficient way to do something, or it won't evolve. It has to be efficient. Okay, so the first thing for minimal function is it needs to perform the needed function. It needs to work. It has to be minimally functional. Minimal function. So the structure or the process must perform the needed function. This, of course, is much easier to explain with the creation by God, because God will design something to fulfill its purpose, and so it will display minimal function. That would be a prediction of creation. So minimal function, first of all, must perform the needed function, and it must be more efficient than what can be achieved with a simpler process or a simpler structure. So the idea of minimal has to do, it's got to be efficient. And actually the simpler the better. So it's got to be as simple as needed for the function that it's to perform. Minimal function. No independent function, that's pretty easy. It means that on their own, the individual parts have no purpose unless they're included or integrated into the whole, and we can't borrow them from some other structure or some other process. They're unique. No independent function. All right, in his book, Darwin's Black Box, the first thing that Michael Behe does is he illustrates his irreducible complexity argument with a very simple device. Okay, I brought one of them. In fact, this is the same mousetrap as in the photograph. This is a mousetrap. And according to Michael Behe, even a mousetrap, which is a relatively simple device, I don't even think we'd even call it a device, would we? We're so used to complicated technology these days. So we can take this. The first thing that we want to do is we want to understand irreducible complexity. So in his book, Darwin's Black Box, Michael Behe chose to use a very simple illustration to help readers understand what the actual argument is. It's important for you to understand the argument before you try to apply it. So we're going to go through Michael Behe's mousetrap illustration and show you exactly what those requirements mean and what the results are of an irreducibly complex structure. I don't know about you, but I don't think of a mousetrap when I think of a complex device. Okay? But it does illustrate irreducible complexity very well. Let me read you a quote from Michael Behe. He says, "An everyday example of an irreducible complexity is the humble mousetrap." What's the first requirement? What's the first requirement of irreducible complexity? Yes? Several interdependent parts. Okay, so with our mousetrap, we have to have several interdependent parts. So according to Michael Behe, our mousetrap consists of one, a flat wooden platform. Okay, so here's the first structure of our irreducibly complex mousetrap. Okay, so it has a flat wooden platform or base. Secondly, it has the metal hammer. Of course, this is the metal hammer, which crushes the mouse. Thirdly, we have the spring with extensions on each side to power the hammer. Fourthly, we have the catch. This is the little part that you stick the peanut butter on, right? Because the peanut butter is sticky, the mouse is not going to be able to snatch it off. Then we have the catch, which releases the spring that snaps the hammer. And then connected to the catch, we have the metal holding bar, which holds the hammer back while you're waiting for the mouse to come and get the bait. So if we have an irreducible structure, according to Michael Behe, he's using the humble mousetrap consisting of the flat wooden platform or base, the metal hammer which crushes the mouse, a spring with extended ends to power the hammer, a catch that releases the spring, and a metal bar that connects. The hammer holds the hammer back. Okay, so here's where he starts his irreducible complexity illustration. You can't catch a mouse with just a platform. So how is this going to evolve one at a time? Could we even evolve a mousetrap one structure at a time? No. Why not? You've got to tell me why not. Why can't we evolve even a mousetrap one step at a time? Why?
The different structures are composed of different materials.
No. Think of natural selection. Yes?
Because you need all the parts to be able to have the thing work.
It doesn't function. Exactly. We have to have all the parts or it won't work. Can natural selection choose my wooden platform? No. Okay, so here's what Michael Behe says. Okay, you can't catch a mouse with just a platform. Then add the spring, catch a few more mice, then add the hammer, catch a few more mice, and then finally add the catch. Do you get the point? You can't catch a mouse with just the platform. You can't catch any mice with just the hammer and the platform. You can't catch any mice with just the spring and the hammer. You need the catch, you need the bar, and what else do you need? I've got them right up here. We didn't even talk about how we had to assemble this, did we? We have to have all these little pieces to actually attach the spring to the platform, the hammer to the platform, the holding bar to the platform, and of course the catch. So something this simple is irreducibly complex. And the whole key is it has to be present as an integrated whole or it does not function. So what's the application to evolution? It can't evolve one step at a time, and that's gradualism. So this tells me that gradualism doesn't work. We couldn't even apply it to something as simple as a mousetrap. Okay, so we're going to use this, and this is a very good teaching tool that Michael Behe used. You can tell Michael Behe is a teacher. We start with a simple illustration for you to understand the foundations of what the concept is and what it means. All right, so here it is again. I'm going to repeat it, go through it again so that you understand what is that, what irreducibly complex. That sounds scientific and difficult. Is it? No, and it's a very good argument. It's a very good argument against gradualism. It's a very good argument against the icon of evolution, the whole thing, who's Charles Darwin. He's the icon of evolution. What's the whole thing that Charles Darwin did for evolutionary thinking? He provided a mechanism. But what this is saying is his mechanism does not and cannot work. It's a big problem. All right, so the mousetrap has several parts. There they are again, the platform, the hammer, the spring, the holding bar, and the catch. And it won't function if even one of them is missing. So we have to have, here it is over here, the integrated whole. The first result of irreducible complexity is complete integration. And then another result was no independent function. What am I going to do with this? Maybe throw it at one of you to wake you up. Okay. Independently, these individual parts do not have a function. So how are they going to evolve in the first place? How is it going to evolve the spring? So forth. All right. The middle result. What are the three results? Complete integration, minimal function, or the need for minimal function, and then no independent function. Minimal function. Could we catch mice a different way? Sure we can. Okay, Michael B., he says you could sit there, stay up all night and shoot it with a BB gun. I couldn't. I would never be able to hit a mouse. But there are other ways to kill a mouse. But this fulfills a minimal function. It's simple. It's cheap. I bought a pack of 4 for $1.97. Okay? So there is minimal function here. Yes, you could buy other traps and so forth, but just because there's other ways to do it doesn't mean that it's not irreducibly complex. Okay, so first requirement, what is it? Several interdependent parts. Just think about the mousetrap to help you understand and apply the argument. We have the platform, the hammer, the spring, the catch, and the holding bar. All right, and then we must have complete integration. All those parts have to be present or the mouse trap won't function. They also have to be put together properly, don't they? Assembly. That's the second idea here, is assembly. And then it has to function. And it has to fulfill the purpose of catching mice. Yes?
And, what do you mean by under several independent parts or steps, the parts must be closely matched?
They have to fit together. These are closely matched. We've got the extension of the spring to match the hammer, okay? You can see we've got the little hook part here that the spring, let me see, I'm not mechanical, but the spring's going to fit in it. Okay, it has to be closely matched. They have to fit together. So closely matched means they have to fit together. All right, so there's the results. Complete integration must be produced as an integrated whole. Here's a way to sum that up. All or none. All or none. The mouse trap is all there or it doesn't function. Minimal function, it has to perform the needed function, and it needs to be more efficient than a simpler means. No independent function, the spring is not going to do a whole lot. If I were to have the spring, it would sit in the junk drawer in the kitchen until I got around to throwing it away. I'm certainly not going to choose it. All right, let's get to the real argument. The mouse trap is not really an argument because mouse traps are not living structures that we are asking how did they evolve. But we do have some very important living structures. Well, blood clotting cascade is first. That's a very important physiological process. Blood clotting cascade. This is another example of something that is irreducibly complex. Now, Michael Behe, in the book, Darwin's Black Box, discussed this. He has received a lot of criticism because they'll poke at it and say, well, this pathway may not be necessary, or this different organism has a different pathway. But all in all, blood clotting cascade is very difficult to answer in a step-by-step, gradualistic evolutionary mechanism. So let's talk about the blood clotting cascade. First of all, you all know what blood clotting is, and you probably all realize how important it is that your blood clots how and when it's supposed to. All right, but what do I mean by cascade? Cascade is a chemical term. It has the idea that one component activates another, which activates the next. It's in a cascade. It's in a sequence. It has the idea of it being a sequence where you have a component floating around in the blood. Do you want that component to be active? No. It'll require another component to activate it. You don't want your blood clotting all the time. And there are people who have blood clotting disorders where one of these proteins is malfunctions, or it's malformed, or it's not present in enough quantities. The blood clotting cascade is a very sophisticated sequence of chemical steps. So a cascade is a sophisticated sequence of steps. It has the idea of one component activating another, which activates another, and so on. So cascade. Obviously, blood clotting is a critical function of the body. You must have a clot form a solid barrier at the right place, at the right time, to stop blood flow. The blood clotting cascade also has to function on autopilot. It is not controlled by the brain. It is automatic. It involves components that are always present in your blood, so that when you have trauma to a vessel and you have leakage out of that vessel, that leak can be plugged. So blood clotting must form a solid barrier in the right place at the right time to stop blood flow. It works on autopilot. It's an automatic chemical sequence. Once it's triggered, it also has to be very precise, and it must be tightly controlled. You've heard of hemophilia, which literally means love of bleeding. A hemophiliac is missing one of the proteins in the blood clotting cascade, or the protein is malformed so it doesn't function. Blood clotting is irreducibly complex. Here's a brief, quick little overview. One of the components in the blood that's inactive is called prothrombin. You've heard of a thrombocyte. Prothrombin is, see the prefix pro? It's a precursor molecule. It will be activated to form thrombin. The thrombin doesn't form clots. Thrombin acts on another protein called fibrinogen. Fibrinogen then will be cleaved in just the right places. Thrombin kind of cuts off the ends and makes them kind of sticky and interlocking. And then you will form a fibrogen mesh, which will slow down and eventually stop blood formation, because how many of you have heard of platelets? Okay, so what you do is you get this fibrogen mesh, and it's going to trap platelets in it and form a clot made of both the fibrogen fibers and the platelets. It's an irreducible complex system. Here's the actual, more complicated version of it. And there's two pathways. Tissue damage, or here's the tissue damage pathway, and here is the blood damage, blood trauma pathway, such as bruising and so forth. Okay? This is irreducibly complex. Now, Michael B., he took a lot of criticism for this, because you can be missing some of these proteins because we have other pathways. This is redundancy. And actually, I think redundancy is a good indication of design itself. Okay, so the blood clotting cascade. You can see on the next slide, this is a diagram from the book Darwin's Black Box over here on the left. And of Pandas and People. That's another book. The author is Stephen Gould. Stephen Gould. Is he a creationist? Does anybody remember what Stephen Gould is famous for? Remember? Punctuated equilibrium. Why? Even an evolutionist of Stephen Gould's caliber knew that gradualism doesn't work. And he actually had a very similar idea and used the blood clotting cascade as well, and also received a lot of criticism. Bacteria flagellum. What are bacteria? They're tiny single-celled organisms. In the case of the bacteria we're going to look at, it is a bacilli. Okay, bacteria is plural, bacterium singular, bacilli plural, bacillus is, so you got to watch your English grammar here with your plural and singular, but bacteria are single cells. In the case that we're dealing with bacilli. And they inhabit some type of fluid, so they need to have the ability to swim. How did that ability evolve? Okay, the flagellum is a long whip-like structure that the bacterium will actually spin it like an outboard motor. It's made up of multiple proteins. That's the first requirement, right? Several interdependent parts made up of multiple proteins that have to be in place for the flagellum to function. And if one of the necessary proteins in that irreducible core is missing, the propeller doesn't work and natural selection will not choose it. Okay? It's just as designed as a mechanical propeller on an outboard motor. It's just as mechanical, just as well designed as an outboard motor propeller. It has multiple parts, and these multiple parts actually have to be assembled in a particular order. Have you ever put together something and you have to assemble it using the instructions in a particular order? Here's the bacterial flagellum. You can see it's got several closely marked parts. This is an actual photomicrograph. Okay, so we're not making up this drawing here. Okay, see that? All right, so is this irreducibly complex? Does it have several closely matched parts? Yes, here we are. We have the filament, that's made up of one protein. Then we have the U-joint, called the hook, that attaches the filament. Then we have the rod, like the drive shaft, going down into the motor. And we even have bushings, spacers to keep it properly anchored to the, well, bacteria has an outer membrane. It has a cell wall, and then it has an inner membrane, so it has a bushing. Okay, I am not a mechanic, but I'm recognizing a lot of these terminologies that were deliberately named to show the parallel to the fact that the bacterial flagellum is just as much a mechanical device or a molecular machine as an outboard motor. It's got the propeller, it's got the U-joint, it's got the bushings to anchor it, it's got the drive shaft, it has the motor, and it even has the movable rotor and the stationary stator. This is bacteria, E. coli. You've all heard of E. coli. It is a type of bacillus. So, is the bacterial flagellum irreducibly complex? And actually, now this is one protein, but look at all the proteins involved in here. Even the motor itself is irreducibly complex. So each part, except for the filament and the U-joint, all of the other parts are made up of multiple proteins themselves. So they themselves are irreducibly complex. And there's a point at which when you remove certain of the proteins, they haven't evolved in sequence, the bacterial flagellum doesn't function. What does that mean? That means natural selection won't select it because it doesn't help the bacterium. All right? And we're not even considering how it has to be assembled in order. That's another argument. The complement cascade. The complement cascade is a sequence of 9 proteins. You can see them. C1a, then we have C2, C4. These proteins are also found in the blood, and they have to assemble and activate in order, and their function is to kill bacteria cells that might be in your blood. This is part of your immune system, the complement cascade, and it is a cascade. It's a sequence of proteins. So that is irreducible complexity. They have to interact in a precise manner in a particular order. So we've got several parts, and they are interrelated. And there it is. If one of the proteins is missing, the cascade falls apart, and your immune system cannot destroy the bacteria in your blood. Could be a problem. This is irreducibly complex as well. Conclusions. Irreducible complexity is a barrier to Darwinism. Why? It eliminates the gradual steps and it cancels natural selection. That's important. It cancels natural selection. It eliminates the step-by-step accumulation. Here's the idea of complete integration. It also then cancels natural selection. We don't have plausible intermediates because natural selection won't choose them. And why doesn't natural selection choose them? Can you guys tell me? They have no function. They do not confer survival advantage. They have no function. Natural selection is blind to them. Here it is. It thwarts the natural selection part of the mechanism. Why? Natural selection cannot choose something that doesn't have a function. There's no survival advantage. And then, of course, it's also complicated by the need for minimal function. If there's a better way to do it, is it going to evolve? Not if it's already good enough. There's those results again. You've seen that same slide several times. These are the crux of the argument. This is how you apply the argument. You must have complete integration. You have a need for minimal function. If it's not going to provide a survival advantage, it's not going to evolve. And then the individual parts have no use. So there's no driving force. Natural selection is supposed to be the driving force. It's not going to act. Okay? There's the summation by Michael V. He himself. Hopefully we've gone through the same several points in several different ways. You're going to understand the argument. Okay, by irreducible complexity, I mean a single system composed of several well-matched interacting parts that contribute to the basic function, that's the irreducible core, the removal, okay, wherein the removal of any one of the parts causes the system to effectively cease functioning. That is irreducible complexity. Now, we did the bacterial flagellum. We did two processes in your blood. Are there more irreducible complex systems in living structures? Or we just brushed the surface. Okay, irreducible complexity. Intelligent design's best argument. We'll see you tomorrow.